Hi, this is our Dynamics Project Part 1, and we are Group 13 with Madison, Glasgow, Veronique Magnan, and Piper Arnold. We all equally contributed to both experiment theory and MATLAB parts of the project because we all worked on them together. Our experiment was performed on April 20th at 1 p.m., and the purpose of our hands-on project is to allow us to use different combinations of balls and plates and find out which ball is going to give us the greatest height. We dropped the ball from a starting height of 18 inches every single time, and then that allowed us to calculate the coefficient of restitution for each combination of plate and ball. The coefficient of restitution is the ratio of final velocity to the initial velocity between two objects after they collide. We use the equations in the lower right-hand corner for this experiment. Real-life examples of using coefficient of restitution are in sports like basketball and golf, or in the game of pool, or even car accidents when two cars collide with each other. The procedure of calculating the coefficient of restitution of a ball and plate combination was dropping the ball from a known height and measuring the height of the next 3 bounces. We then took the square root of the second height over the initial height to get the e-value, and then repeated for the third height over the second height to get another e-value, and then took the averages. The goal of this experiment was to determine which ball and plate combination produced the maximum coefficient of restitution. Our expectation was that the best combination would be aluminum and nylon, and that the worst would be acrylic and wood. This is relevant to our majors because as mechanical engineers, we're often responsible for designing projects that may have this occur, such as accident modeling, and as civil engineers, the coefficient of restitution could be used for designing certain areas of construction that civil engineers are responsible for. For our experiment, we used the combinations of a nylon ball aluminum plate, Delrin ball and aluminum plate, nylon ball and acrylic plate, and Delrin ball and acrylic plate. We found that the max e-value was the nylon ball and aluminum plate of 0.92, and that the minimum e-value was Delrin ball and acrylic plate of 0.83. For each ball and plate combination, we dropped the ball from an initial known height of 18 inches. We then slow-mo recorded the ball bouncing 3 times, and then we found 3 different e-values for each combination and took the average. For exercise 2, we decided to use the combination of nylon ball and aluminum plate. We couldn't find any relevant literature sources that fit our exact scenario of ball and plate. Error may have been caused from the initial height not being exact every time, or the ball may have not been bounced perfectly vertical. These couldn't have been avoided, but they may have been made smaller by us lining up the exact center of the ball with a ruler at 18 inches, and discrepancies between theory and experiment may have been us from assumptions we made, and that in theory the e-value would have been calculated perfectly, and we may have had error in reading our height values.
This is Group 13's Dynamics Project Part 2. Madison led the presentation, Piper led the MATLAB coding, and I led the hand calcs, but we all contributed equally. And this experiment was performed on April 20th at 1 p.m.
Projectile motion is the motion an object faces after an initial force launches or projects it into the air. Some examples of why projectile motion is important as it can predict the path objects will take. NASA uses projectile motion when predicting the path meteors are on, and it can also be useful in sports to get the optimal angle for a distance and location that is being aimed for.
To start our test procedure, we picked and measured the angle that was going to be tested. Then second, we measured the height from the plate to the ball drop location. Third, we placed the obstacle in the current location using the ruler and level. Fourth, we placed the ruler where it could be seen. Fifth, we started our slow-mo videos and dropped the ball. And then sixth, if the ball cleared, we measured the max height and lowered the angle, and then we repeated the steps again.
Our derived equation for if the ball will clear the obstacle given at the angle and coefficient of restitution given is shown below. The range of angles that worked for our combination was 8 degrees to 29 degrees, and the angle that gave the maximum height of the ball was 8 degrees.
We were able to clear the obstacle using the nylon ball and aluminum plate and got a max height of 13.89 inches at an angle of 11 degrees. There was a difference of less than an inch from our numerical calculations and what we found in our experiment. This is most likely due to the averaging of e-values instead of using the singular largest value from the first bounce. We also did not account for air resistance, which may have also contributed to the difference in max heights. The graph comparing our calculated values and experimental value is shown below.
After completing this project, we can conclude that our experiment was successful because we found a maximum height that was within half an inch of our calculated value. This project allowed us to conduct a real-life experiment which gave us a better idea of how concepts including projectile motion, impact angles, and relating velocities can be applied in real-world scenarios. Possible sources of error include not accounting for air resistance, averaging the coefficients of restitution, and the ball not hitting the plate in this exact same spot every time. Some of these errors could have been minimized by using a better system for reading the heights and being more precise with the obstacle placement.